I think all of us are interested in improving the state of the art in robotic technology, and all of us sort of came around this idea of, humanitarian rescue robots. We want to send these systems out in the field to save lives. Florian is over 6'2" now, probably 350, 370 pounds, about 170 kilograms. So he's a big middle linebacker, for a football team. The Atlas is primarily a hydraulic system. It tends to be a bit bigger than some of the other electric robots, and so that has its own challenges when you're trying to fit through a door or fit into a vehicle. The group of us have been working on improving the software, adapting to the changes to the Atlas robot, and improving the performance toward the finals that are coming up.
You could say it can do everything a human can do, just slower and not with as much dexterity.
It's a humanoid platform, which means it has to balance on its own. So the robot has to continually balance as it's stepping and walking. So that's one disadvantage to the humanoid platform. If the robot falls in a certain way, it's going to rip an arm off, and there's nothing that can be done about that. The advantage is you can maneuver in human environments a little bit easier, go upstairs, navigate rougher terrain potentially than a wheeled vehicle might.
Sending right arm to stand.
So we have a ton of sensors a few sensors on the robot. So we have a stereo camera that gives us images and also depth information. And then of course we have our custom hand cameras. So we can actually look with the hand, which is a modification that you, for example, can do that a human can't easily do. You can't look with your hand as a human, but our robot can.
We also have some cameras in the top of the head, pointing to the sides.
Two fisheye cameras give us this wide field of view situational awareness info. Because that's another thing that is maybe not perfect about Atlas. The head can only pitch. It cannot see to the sides. We have a LiDAR scanner that is spinning and gives us very accurate distance information.
This is the LiDAR sensor. It shoots a scan of laser beams out, measures the distances to objects, and it spins around, so it gives us this big point cloud. So now you see, as the LiDAR is spinning, you see it building up this 3D view of the world. Magic.
So as we move around, you actually get a 3D view of like a room, for example. But we can't really look backwards right now.
It's constantly an issue of trying to maintain situational awareness because the robot can only see forward. So we have to get a map of the world as we approach, and then we turn, and then we have to make sure that what we're seeing on the screen is actually how the robot's really aligned with the world.
Well, we improved the operator station interface, so we are better able to see what's happening.
So this is the main view screen, and then this is a 2D projection, what we call map view. The same view of the world just from the top down. Gives a perspective of how the robot's going to trace out as it's moving. And then this is the video feed, so we can do different camera views to show what the robot's seeing from the camera. Go for it.
We focus on teaming up the operator with the robot, so we consider both teammates that have to work together.
So changing left arm.
This is an overview of our main operator control station. Spiros is managing the high-level, task-level behaviors in operation. Then we have two operators that are concerned with maintaining situational awareness, perception of the world through the robot's eyes.
Okay, we're standing.
And then placing templates into the world that guide how the robot will execute certain tasks.
Sending right arm to calibrate position. Right arm showing in camera.
The strategy from the beginning was to be able to allow the operators to flexibly direct the robot.
Sending left arm.
So what basically happens is we walk into a room, we have a valve that we want to turn, that we discover. We put in this valve template, this object model, put it over the sensor data.
You can see the template that they've placed in the world, and they can manipulate that template around to allow the robot to adapt to the offset. So knowing where the operator says is this is the best spot for this template, it tells the robot how it should grasp a particular object. So in order to move its arm from its side up to a position to grab the valve, it has to coordinate motion among at least 7 joints. And so that kind of planning, that's all happening on board. And so you let the humans do the things they're good at and then provide task level direction to the robot, and then the robot's internal software is doing the calculations of, okay, here's how I control the joint, here's what forces I put on the joint in order to move the arm.
I mean, a single wrong arm movement or so can flip your robot over. The thing is, these robots are big and heavy and strong, but they don't really have a sense of touch, at least not a very accurate one.
Confirm. Confirm, going for the door.
Okay, starting to walk.
Our operator control station is designed to let the operators direct and interact and then to adapt to any kind of problems that we may see during a run.
Okay, left arm looks okay, near the wall, but...
We use the 3D model of the world to place our feet, or the robot's feet obviously.
This was the footstep plan of the robot as it was walking and turning, so they're checking the path that the body's going to trace out as it moves and try to see that that's clear of the wall and the valve rack.
Oh, okay, fall. Yeah, well, I mean, we try to not fall, of course.
Walking is generally okay, and then sometimes it fails and you're never quite sure why. So we've basically tested on delay because given hardware issues and limited spare parts, we can't risk the robot. If the robot falls and breaks an arm or a joint, you're losing half a week before you can get it repaired. So at the trials will be the first time we're walking around off belay.
Execution complete, tilting head down.
Okay, looking down. Torso to far right.
We are confident that we can do well. I think we could have done better at the trials. There were some issues that we encountered.
Okay, complete adjustment.
No, I think we were, devastated would probably be the right word. We really felt like we underperformed at the trials.
Torso to far right.
Our software was better than we showed it.
I don't want to go overboard with we'll win it, nobody else has a chance, but we feel we can do good, and that's what we're going to do.
We're in this because we love the technology. I think, to win, I think it just sort of, validates 2 years of our lives of hard work, but Florian is an impressive machine. It's a lot of actuators, a lot of power.
Perfect. Okay, go for it.
It has a lot of capabilities, and, we're looking to try to exploit as many of those capabilities as we can.